All right, the next section we have is the trigonometric limits, and in this section there is a particular theorem that is extremely useful and robust, and it's going to help us throughout the course, and this is the squeeze theorem. So the squeeze theorem, the text of it is right here, but we can just take a look at this sort of example here that will help us understand what the squeeze theorem does. So this really curvy function right here, that is x sine of 1 over x. Okay? So if we want to know what the limit of this is as x goes to 0, so visually we can see that the limit should be 0. But if you just had, an algebraic expression for it, so for instance, if we had the limit as x goes to 0 of x sine of 1 over x, well, what ends up happening here is we can't just plug it in. Because if we plug it in, effectively what ends up happening is 1 over 0 is undefined, right? So if that's undefined, we know that what happens as x goes to 0, this fraction right here, 1 over 0, becomes very large, so it goes to, becomes unbounded as x goes to 0, from the right at least, and from the left it goes to negative infinity. And then sine is always a number between 1 and 1. So what's interesting here is this, although inside the argument gets very big, all that does is change how quickly it oscillates. So this term right here should be between negative 1 and 1, always, but this term here is going to 0. So we can't actually evaluate this by direct substitution because it's not continuous at that location. Clearly, if we plug in 0, we run into issues. So this function is discontinuous at x equals 0. So the way that we calculate such a limit here is we first figure out, through some algebraic means, that this expression, x sine of 1 over x, is actually between these two functions. It's between the negative absolute value of x, that is this upside down triangle. So sorry, it's above that absolute value, and it's below this absolute value, which is just regular absolute x. So since this graph is always between the two, we can go ahead and write down this inequality. And then, as with any sort of inequality or compound inequality, we are free to perform some legal algebraic operations to it. We can add something to all portions. We could add 2 to each side, and even in the middle. We could divide by 5, we can multiply, we could do lots of different things. In this case, the operation that we're going to perform to each portion of the compound inequality is we're going to take the limit as x goes to 0. So when we do that, we don't know how to do the limit of that middle portion, but we do know what the limit of negative absolute x is and the limit of absolute x, because absolute value of x and its negative are both continuous functions, so we can evaluate the limit by direct substitution. In other words, just by plugging in the value, x equals 0. Well, we get 0 is less than or equal to this limit we're trying to find, which has to also be less than or equal to 0. Well, there's only one real number that is greater than or equal to 0 and less than or equal to 0. The only thing this could possibly be is 0. So effectively, what this does is it squeezes this limit to having only one possible answer. Geometrically, the squeeze theorem is a little bit easier to see, that it actually takes this graph and sort of compresses it as you go in closer.